Hello everyone, my name's Alistair. I'm one of the many Western Digital people here. Um, yeah, we were talking at lunch. I think I'm the person who's traveled the furthest ever for Lund Linux conference. I came from Brisbane, Australia. Um, yeah, so it was 24 hours in total to get here. And today I'm going to talk about RISC-V and QEMU. So mostly QEMU, because QEMU is great. So this first slide, this is the 0th slide. The first slide, the one after this, I don't really like. I only put it on because I was walking home last night. I was like, I'm going to put it in. But next year, and every time after this, it won't be there. So we won't need it. What is RISC-V? I think most people probably know. I think everyone's kind of heard of RISC-V now, but I thought I'd put it in. So the first thing is it's RISC-V. It's not RISC-V. And so what it is, it's an open ISA. So it's the instruction set architecture, right? Not a CPU. Doesn't mean your CPU is open. It just means the whole, the ISA is open. It's different to the other kind of major architectures you're thinking of that aren't open, and so RISC-V is. And so the way it works is the base ISA is very, very small. It's kind of useless, but it's very small. And you add your base extensions on top of that. So, atomics, multiply, that's an optional extension that you add on top. And then you get the bigger ones, so the virtualization, which allows hypervisor support, and vector extension, which is, does vector acceleration and things like that. And RISC-V is not, I think people think it's just, just for academics, just for university. It's the whole scale, so it's embedded all the way up to HPC. And if you look at what the Barcelona supercomputing group, they're looking at putting RISC-V into hyperscale computers, and there's lots of embedded people using RISC-V right now. So it's the whole platform. RISC-V will overtake everything. Sorry for the people who work at other hardware companies. And it's backed by a lot of companies, including Western Digital. So what is QEMU? So I think most people, have heard of QEMU, have probably used QEMU, but it's kind of bigger than I think most people think. So it's a very quick, it's a key part, very quick emulator and hypervisor with an asterisk, and that's the next slide, the kind of hypervisor. And so it's not cycle accurate, it's functionally accurate. So in the case of RISC-V, you can run your whole RISC-V stack on QEMU. You can run the same image on a board and on QEMU. It's going to match it in terms of functionality, but it's not going to give you the same cycle performance. It's not going to, on the board, maybe you miss caches, and so you have a slowdown. On QEMU, you don't get that. It just runs as fast as it possibly can. So it's not a simulator. It uses this thing called TCG, so Tiny Code Generator, and that translates your guest architecture, so RISC-V in this case, onto your host PC. So eventually that'll be RISC-V as well, but for now it's still x86 or something else. And there's 2 modes for this. So there's soft MMU, which is a full system mode. So you start up with your firmware in machine mode that boots to your kernel in supervisor mode, which starts up an MMU. Maybe you have a hypervisor and you have a 2-stage MMU. Then you run user mode. It's the full system: interrupt controller, interrupts, timers, everything. And then you also have this user mode, which works on Linux and BSD. And that's where you have your RISC-V application, so something I've built to run on my RISC-V CPU in Linux. And I can run it on my host PC, and it translates the instructions from RISC-V to your host, and you use the host's kernel as the system calls. So you can just run user-space applications without a kernel. And so that's used a lot in compiler testing. So if you're a GCC person, you build your application, and then you run it on your host PC. TCG, or QEMU, is also open source, and it's supported by multiple companies, multiple individuals, multiple people. It's not it's not just Western Digital. It's it's everyone, and it's very similar to Linux, mailing lists and that type of stuff. And this is QEMU, the hypervisor. It's not really a hypervisor, but and so this is on RISC-V. So we have machine mode down here where you run your firmware. Then you run your Linux and your KVM in your hypervisor mode, and that's the actual hypervisor at KVM. And then QEMU in user mode, And it's what the user would interact with. So you run a QEMU, so that's all you kind of interact with. But it runs the guest IO emulation. So we emulate the interrupt controller, for example. It's called the PLIC, and then VirtIO backends, things like that. So QEMU is not, it's not the hypervisor layer itself, but it kind of is exposing a hypervisor, and then you can, run all your virtual use cases. And I have a demo at the end. And so the basics of TCG. So TCG has this very famous diagram or picture on Stack Overflow from QEMU 1.6. So we just released 7.0, so it's a bit out of date, but it kind of goes through all the ways that QEMU generates instructions for your target or your host architecture. So I'm not going to read through that. If you're interested, you can go read about it. But basically, TCG takes your guest code, does a little bit of live list analysis and very little optimization, sticks it into a TB block, which is like a bunch of guest instructions, and that block ends at a jump or a branch or certain CSR accesses or things like that, and then it translates them to pretty much, you can see down here, pretty much any architecture you are interested in. So, and there's a picture as well later on of what this looks like. So that's a kind of higher level overview of QEMU. So now, how great is it? So in the early days of RISC-V, there was no hardware, right? So it was designed by academics, and the instruction set existed, and everyone was excited, and everyone wanted to use it, but there was no hardware. So what are you going to do? So everyone uses QEMU. So Linux supports the QEMU virt machine. Every project that targets RISC-V supports some sort of QEMU machine. But now hardware is getting a little cheaper. You can find some things. Do we still need QEMU? Yes, is the answer. And QEMU is free. So that's the most exciting part. It's not cheap, it's free. So, and to give you an idea of speed, QEMU is going to be faster than pretty much any FPGA that you have. I said that once, and someone really got annoyed and tried to call me out on it and wanted proof. I don't have proof, but you can kind of tell when you run QEMU compared to an FPGA that it's faster, and it's basically always faster. And it's always available. So whatever distro you're running, just apt install, DNF install, whatever you're doing, just install QEMU, and you can be up and running. And so this is a picture from 2019 we have at WD of a Sci-5 board, a PCIe expansion board, a hard drive attached, 2 PCIe cards to get USB and graphics. And we can run a GNOME desktop system on this thing. It's about 30 centimeters long. It's extremely expensive. It was a nightmare to move it around to show it at demos because of customs. And instead today, we can just use it in QEMU. We have the whole thing running. It's probably faster, if not the same speed, depending on your host PC. And everything works. So, and we've had talks yesterday, I guess, about the importance of CI, right? The Google Chrome, the Chromium guy was saying that what's important is testing, and so that's where QEMU also really shines. So let's say you work for a big company and you have all this money and you go buy every developer a board on their desk. That's great, but then you go to run a CI, and okay, maybe you can afford the boards. You buy some more boards and you stick them in a server, but then you need a guy who has to go and turn them all on and off every now and then, unplug the cable, replug the cable, turn the aircon on, change the temperature. It's a mess dealing with a board farm. So QEMU is just a virtual board farm. And so we use this in the TOC project. So TOC is an open source embedded operating system written in Rust. So I know everyone loves Rust. So written in Rust, and on every single pull request, we fire up QEMU and run it through a test case or multiple test cases and look at the output and what happens. So at every single pull request, we're making sure it runs on RISC-V. There's no board farm. We're just using GitHub's free, self number of minutes and all that stuff. So it doesn't cost us anything. There's no maintenance. It just runs on QEMU every single pull request. So we never have a regression. It doesn't mean you can get away. Maybe you still need some board farms. If you have a bike and you want to make sure your bike still works, but you can offload a lot of it onto QEMU. And you can use QEMU. This might be a bit bit far out for everyone here, but you can use QEMU to develop RISC-V extensions. So when you eventually come over to RISC-V and you start developing extensions, that's where QEMU also shines. So you can see here, that's kind of the output of QEMU, the translation blocks I talked about earlier. And QEMU, it's a lot easier to add instructions or add CSRs or add features in QEMU than it is in an FPGA or a simulation. It's, adding an instruction is actually just some Python code now. It's pretty straightforward. And a little bit of C, a little bit of C and a little bit of Python, but it's pretty straightforward. So you can quickly add an instruction, rebuild QEMU, and boot Linux in under 30 seconds. And so you can test any change you want in hardware or software, over and over again as quick as you want. There's no bitstream download and license checks and all this stuff that you have to do with other things. And for real debugging, if you want to actually connect GDB, you can run QEMU with -s, so lowercase s, uppercase s. And I forget which one's which, but one is stop, like QEMU doesn't run, and one is exposed GDB port. And GDB client can connect to the GDB server, and you get full debugging. So you breakpoints, watch points, register reads, memory writes, CSR accesses. And so this is a screenshot of me debugging OpenSBI. You can step by step, you can see all the registers, you can see the PC, you can see it's got 4 CPUs running, you can see back traces, you can see everything. So QEMU allows you to get all the information in the system. And so, you have a board and your board has JTAG, you're thinking you can do the same thing on hardware, right? You can, yeah, but you have to get that special vendor device that costs more than the board and plug it in and then wiggle it just to get the cables to work. And then you try and use it and you realize the driver only works on Windows. So you get your Windows laptop out and plug it in, and then realize the driver only works on Windows XP. And so then you have to go get a Windows XP laptop. And none of that problem with QEMU. It just works, you just connect it, you've got all the information, what else do you need? And if let's say you're not really thinking and you hit continue instead of step, exit out, restart, you're back at the same spot in 20 seconds. So QEMU is quick. So QEMU status, when I say QEMU status, I more mean RISC-V status for QEMU. So QEMU supports all of those extensions. I'm not going to read them all out, but that's all of the extensions, and that's already wrong. Since I've prepared these slides, more extensions have been merged. So that's vector extension, hypervisor extension, PMP, we even have draft extensions like the advanced interrupt controller, which isn't even ratified yet. We have patches on list for the IOMMU. RISC-V doesn't have an IOMMU. There's no spec out yet. Well, it's kind of out. It's in draft, but there's no published, fully announced spec. Yet we already have patches on list in QEMU, and we'll actually probably merge them before the spec comes out. So if you want to use RISC-V and you're waiting on that board, just use QEMU. And we also have vendor extensions. So I've got a slide about that, and we'll see what everyone thinks about that, because vendor extensions are a bit touchy. But we have 32, 64, and 128-bit CPU support. So 120 bits a little, quite experimental, but it is there. And we have contributors from every kind of major RISC-V company and a lot of others. So I didn't list them all. So a little more technical part now. So this is the RISC-V hypervisor extension. So this is what we use to run KVM, or there's no Zen port, but Zen or something like that as well. And I have a demo of KVM on the next one. So I think everyone's kind of used to, user privilege modes, right? I think most architectures have those. So you have, firmware, your operating system, your supervisor, and your user mode. So RISC-V doesn't add a fourth mode like another famous architecture does. We kind of split the architecture, the modes in half. So machine mode stays the same. It doesn't have a hypervisor or anything. And your HS mode, where your supervisor normally runs, where Linux runs, has a HS mode if you have the virtualization extension. So you can boot up on a system and never use it, and it just acts like a normal computer, right, or a normal system. Or you can run KVM there. You don't have to leave a little trap or stud you come call back to. It's all in the same mode. And then we have user space, non-virtualized user space, and we can swap into virtualized mode. and we swap the registers around on, well, the hardware swaps the registers around on traps. And so we get these new CSRs with these, these VS CSRs, these virtual CSRs. And when we swap between virtualized and unvirtualized mode, the hardware swaps them around. So we can run unmodified guests, obviously. And so here is a demo that hopefully everyone can see. I pre-recorded it because I didn't trust it to work. Oh, can I hit play? There we go. But I've got to remember what I did now. That's the only problem. Oh, it's me talking. I'm just going to read it out because I think it's easier. So this is QEMU RISC-V, so running on my host computer. I don't know what I'm saying now. Yeah, so it's all the kind of standard arguments you'd expect. So we're exposing a network device, we're forwarding SSH ports, we're exposing the host PC's randomness, we're attaching a open embedded rootfs that I built via block device, and got some fun little tablet things in there. The virt machine, which is the main machine, 4 cores, 2 gigabytes of memory, serial, nothing exciting. And we're running the next one, I'll click on, there we go. We're running OpenSBI, so that's the common RISC-V firmware, kind of similar to ATF. And then we're running a 5.18 kernel, because that's what I built. There we go. So that's OpenSBI. Version 1. It's detected, this is all device tree based, right? So it's automatically detected this. This is the same image I run on a sci-fi board. It's 4 cores, it's detected all this. That's the next address I'm going to jump to. I'm going to jump to S mode. I've got the hypervisor extension enabled. It's enabled by default in QEMU. And I'm sure I'm saying something else there. There we go. And now 5.18 kernel. And here's Linux. So it's detected SBI, and it's detected KVM, when I find it. There we go. It's detected KVM and the hypervisor extension. So the kernel has automatically detected KVM, it's enabled it, we're going to use it when I scroll down a bit more. Otherwise, it's just a normal Linux boot. There we go. Systemd. I like Systemd as well, like the Bosch guys were saying. So log in. So now I'm going to paste in, I'll show you there's 4 CPUs. We call them hearts in RISC-V, but 4 hearts. Each one has the hypervisor extension, 64-bit. There we go. Okay, so I'm going to run on my RISC-V QEMU instance. I'm going to run another RISC-V QEMU. No graphic as well, no monitor, just the virt machine, same machine, SMP1, 64 megs of memory, just using less. The exact same kernel image. It's the same 5.8 kernel image copied into my rootfs, exactly the same. I'm using a different rootfs, just a little build root one, just to save space. And then I've got enable KVM. So we're running with KVM. So I've got x86 with QEMU and the QEMU instance inside that. And you can keep going. And you can see it's too quick, like it's already booted. I couldn't even, so 5.18 kernel, and yeah. So this one doesn't have KVM. We actually, I said we can keep going, but we can't. But we don't expose KVM again. That is possible. It's just we don't support it yet. And that's it. So here we go. Here's my build root, my RISC-V virtualization running on QEMU. No hardware can do this, or no public hardware at least that I've seen can do this. So it's all only in QEMU, which is pretty exciting. I think that's the end of the demo. I think I just exit out now. Yeah, because we don't expose. So here we don't expose the hypervisor extension, and it might be different other extensions because so we just, it depends what we understand in KVM. Oh, exiting out. So this is back to my 4.1, and then I'll quit. Oh, and this is QEMU 7. So this is released. This is not my fork. This is not some vendor tree. This is what has been released, what's enabled. If you DNF install or Pacman install, this will be there. So, did that work? Or was that playing again? Oh, there we go. Okay, so this is the vector extensions. this is a big deal in RISC-V world. So I gave this talk at a RISC-V thing before this. This might not be as exciting for everyone else, but I think it still kind of shows QEMU, and vector extensions are all the rage. So oh yeah, again, the 7.0 release. I'm a little slow though. There we go. 7.0. It's just got actually some extra patches on top because I was using master, but okay, so Vert machine again, CPU RISC-V, 64-bit. This time we're enabling the vector extensions. There's too many extensions in QEMU that we kind of don't enable them all the time. So vector extension is disabled by default. So we're enabling it with this v equals true. SMP1, just 1 GB of memory. And then the cool thing here is I've disabled all the serial and all the output. So there's no UART output or anything coming from the guest. And then I'm running no OpenSBI. I'm just running my ELF application in machine mode. So it's just a bare metal, no MMU, nothing fancy, just machine mode thing. And I'm printing all the interrupts, all the exceptions, all the interrupts that occur, I'm going to debug output. And then I'm running with semi-hosting. So semi-hosting is defined in the RISC-V spec, and other architectures have them too. But basically, whenever we see an e-break, which is the kind of debug break assembly, and we have a no-op before it and no-op after it, and these special no-op instructions, QEMU interprets that as a system call. And so by enabling this semi-hosting, when I run this e-break, QEMU gets a system call into it, and the guest can then do things. So that it can exit with a return code, or it can open a file, or it can open standard out and write to it. So that's why there's no UART. The guest in here is not touching any hardware registers. It's just doing system calls to print the output, which is just because I was lazy. That's the main reason to do this. It's just easier. There we go. So vector version, that's just QEMU telling me that it's using the 1.0. So we have different versions of vector extensions, and 1.0 is what we're using. And then everything else is printed from the guest. So the guest is doing system calls to print that information out. I can't remember what I'm saying now. I'm probably something smart, but okay, so this is the vector code that I'm running. So it's based on this guy's GitHub, and then I've made some changes to it. And so we're running through 2 tests. So we're doing a mem copy, with just a libc mem copy, and we're doing a vector version mem copy using the vector instructions. So you can see here that I'm kind of running it twice. So I'm doing it the first time and then the second time. And then the reason for that is because QEMU caches instructions as it generates them. So the first time you run an instruction, it can be kind of slow to generate it. And so if I don't do this, what I realized happens is memcopy just uses loads and stores. And so they were all cached. And the vector uses these fancy vector instructions that had never been run before. So they weren't cached. So they were significantly slower. So I tried to just even it out by running everything first. And then I run it again with my, my prints, so then we can read it. And so I'm just printing the time, like the number of cycles that before and after. I don't know what else I'm saying. It's probably how cool the vector extensions are. Yeah, so time and RD cycle. So that's a vector extension. That's what the assembly looks like. So it's this vset VLI, and then vector load and vector store. And that vset VLI sets kind of all the striping and sizes and everything for vector. So I'm not going to go too many. We're not going to go into any details about that. But so that's what I'm running. And then, this is the actual object dump. So so I can talk about this, I guess. But so the object dump, I can look at the old mem copy and the new vector one, and I can see the old ones. I think like 23 assembly instructions to do the copy, and the vector one's about 13. So you can already tell the vector is significantly less instructions, so it's smaller binaries. But then also, yeah, that's pretty much it. That just takes all this time to say that. It's the only problem with pre-recordings. You can't kind of like click through it. Yeah, so that's 23 there, I think. And so this is my, Yeah, so this is the same thing. This is the vset VLI, and then vector load and vector store. So I've said before, right, QEMU is not, it's not a cycle accurate, right? So when I run this, you're comparing, you know, it's not exactly the same as what's going to happen on your CPU. So if your CPU takes 5 cycles, or 5, you know, clock cycles to do a vector operation, obviously it's a different output than what it is in QEMU. But it still gives you, I think, a reasonable idea of, especially on a RISC, right, of what it should look like. And so this is what I'm showing here. So you can see, we can look at the number of cycles that happen between the vector one and the mem copy, and then we can look at the number of cycles, which is about, I think it's 3,500, and then we can look at the number of cycles between the vector copy, and it's, you know, 500 or so. So in QEMU, we can see it's faster. So it's not super easy to extract that out to what that acts like in hardware. But if you were, say, trying out different things in software and seeing how that works and is this one faster or not, QEMU can be useful there. So it obviously depends on your hardware implementation in the end. I think last time I gave this, people kept asking me like, oh, can I model the cache? And then it's not what QEMU's for. So QEMU's for being quick. Oh yeah. So vendor extensions. So this is this does affect Linux as well, because Linux is doing the same thing. So how do we handle vendor extensions? So the cool thing about RISC-V, right, the reason we sell it to companies and people is because you can add your own instructions, right? So that's the cool selling point. You can modify it. There's no NDA, there's no nothing. But then if software says we won't take vendor extensions, then we've kind of ruined the benefit. So most open source projects are now taking vendor extensions. So QEMU is, and we have one. GCC and LLVM are, and I think the Linux kernel is heading there as well. So I don't know, if people are interested in RISC-V, this is something that I think we're just going to have to handle. In QEMU world, we're trying to kind of isolate it. So the idea is we have one file basically per vendor. And you know, if they ruin their file, that's their problem. But then we keep it isolated and we don't have to come back, you know, and modify everything. We'll see how that actually goes, because once CPUs, you know, once vendor extensions actually change CPU state, that might fall apart. But, and this is just, I don't know, I don't think anyone's here is a RISC-V vendor extender. But if you are, this is how you do it. You basically just write some you know, these easy to read decoder files, and then some C implementation, and you build it. And there's examples in mainline of how to do this, and we're working on adding support for the new CSRs. And that's basically it. That's just how to get involved. It's a mailing list, so send patches, but most importantly, review. If anyone's interested, go and review the review code. So, any questions? Yeah?
At the very beginning, you were showing a T connected to QEMU.
Yeah.
It's really good. What
The GDB one?
Yeah.
Yeah, that's just,
What is that?
where did I get it from? I didn't invent it. I downloaded it from some guy's GitHub.
Dashboard, I think. I use the same.
What's it called?
Dashboard.
Dashboard, yeah, GDB dashboard, that's it. Yeah. So yeah, it shows you, and if I had source code, this is old, but if I had the source code, it shows you the C code as well, so.
Thank you.
Any other questions?
Have you had any issues because it's not cycle exact?
Yes.
Yes.
Yeah.
So because you still need the additional testing, but for
Yeah.
first line of defense testing, so for CI it's very good. So
Yeah. I mean, the problem is anything cycle accurate is super, super slow.
yes.
So.
Or physical hardware.
Or physical hardware, yeah. So realistically, I think you don't really use any. Oh, it depends. It depends what you're doing, but yeah, that is a problem. But
Because even open stack testing has run into trouble where QEMU just works, and if you try the physical hardware, it just breaks.
we definitely do see that. I mean, yeah, it's not going to catch everything. So
No, but it
yeah.
catches enough, but you still have to have the extra.
Yeah, it does. Yeah. But it also, I mean, the other problem you have is there's physical hardware that doesn't meet spec. So, I mean, that's also the other problem. Just because it works in QEMU doesn't mean it'll work everywhere. But, I mean, what are you going to do about that? So,
How do you avoid wild organization of different vendor extensions? Like, how does the ecosystem deal with that?
yeah. We have a plan. We'll see how it goes. But basically, the idea is that vendor extensions are disabled. So you just enable each one. And then that means, because vendor extensions should all be in this, the same kind of code space. So if if you just enable one, and that's the one you're interested in, that should be okay. But then, I don't know, if vendors start having conflicting versions and all this stuff, it's...
And I've never done that.
Yeah, so, yeah, I don't know, it's a hard problem, but I think for a while we just said no vendor extensions, it has to be official, and now I think we're going, well, it seems a little unfair, because what's just going to happen is everyone's going to have a fork. There'll be this company's fork, and this company's fork, and this company's fork, everything, Linux, GCC, QEMU, everything will be forked. And I don't think that's better, so I think we're going to have to deal with it. So, yeah.
So a lot of the instructions for RISC-V are optional, but if RISC-V is going to take over the world, what does that mean for the portability of RISC-V bindings? If I cannot assume, for instance, that it has double floating pointer tables.
Yeah, so that's a good question. It's a common question. So basically, the plan is to define these. The RISC-V Foundation calls them profiles. And so there's an RVA, so a RISC-V application profile, and that's what Linux will use. And the profiles say, this is what you need to do. And so you need to have floating points, and I can't remember what else is in there, all the kind of standard atomics, all the obvious ones, and then also these ones. And the idea is that, and they come out every few years, I think every 2 years. And so the idea is, your hardware will say, I'm RISC-V 2022 compliant. And then Linux can just, anything that's 2022 compliant, is going to have floating point and whatever else. And so that way, you're only kind of targeting almost like major versions, right? Like other architectures do, they have, every generation, almost like you're targeting these generations. So that's kind of the plan. On the kernel side, there's also talks of how we handle, because some of even the profiles, vector extension is optional, right? So you might have it, or you might not. And then if you do have it, how do you handle that? You don't want to do a check every time you do a memcopy. Do I have this extension? Yes. And the checks can be quite slow, because sometimes you have to call down to the firmware, right? So you're actually doing a full context switch down the firmware and back. You can't do that every memcopy, right? That doesn't work. So there's talks of live patching code, so you modify the code at boot to use it. All that depends. Like vector extension, the kernel probably won't use, is my understanding, and it would just be is user space using it, and then we have to do save restore of user space vector registers. But yeah, so yeah, that's a hard problem too. But I think the answer is kind of profiles and software maybe setting some rules and saying please do this, or it'll hurt.
Yeah, it just seems like it could get out of hand.
Yeah.
Quite quickly.
Yeah. Yeah, so I think profiles are one of the ways of fixing or helping stop that. Is that it? Anything? Okay, cool, that's it then.